All right, thanks. I could talk about the OCaml installer for Windows and how of a delightful experience it is to maintain it, but instead I'm going to try to talk about something more fun for me. I don't really want to talk about Windows right now. Okay, so this is some news from the FStar team, which I am now a part of, and this is a big piece of work that involves several people. Perry Wang from MIT was our intern this summer. Abhishek Anand from Cornell was our intern last summer. We have our friends at INRIA, Karthik and Jean-Karim, and we have a bunch of people at Microsoft. So one tendency that I've noticed in conferences of these past few years is that the hot new thing these days is to translate to C. Everyone's talking about C, and everyone wants to be a hipster C hacker with a beard. So there was Bedrock a few years ago, right? You do a deep embedding of C into Coq, and then you prove functional correctness of your program, including memory safety using the proving power of Coq. And Bedrock is pretty expressive. You can talk about addresses, pointers, and then you can do things such as a cooperative threading library, advanced data structure. So it's pretty powerful. But there's, even as recently as 2 days ago, we saw Cogent, which is a DSL using a combination of type system features such as linear types and polymorphism to generate some C code. And the safety is proved through a shallow embedding into Isabelle. And it's great. They've done some systems code. They've done file systems for the Linux kernel. So really, it's the new thing, right? There's more projects that are about generating C, and FStar, wants to be hip as well. So FStar is going to generate C, and that's what I'm going to tell you about during this talk. So the first question is why? Why do you want to go to C, right? The reason is we have embarked on a big expedition to do a certified TLS library, right? So that's an excerpt that I found in a paper, and the author is talking in a very jaded way about how there's many ways that TLS is broken. I should probably remind you that TLS is the transport layer security, the security protocol that allows you to have secure communications on the internet. So TLS is broken in two ways. The protocol itself is broken. That's when you have the client who goes talk to the server and says, hello server, I would like to set up a secure communication, and the server says, well, certainly, here are my cryptographic parameters and my Diffie-Hellman shared secret, and the client says, sure, what kind of protocol version would you like to use? And there's like a whole, little talk that happens, and that's the protocol version, and that is, flawed at the design level. And there's also flaws in terms of implementations, because OpenSSL, for instance, is written in C, and it has like the usual buffer overflows and usual coding mistakes. So we're going to do better. We're going to generate C. Wait. So yeah, one of the constraints that we have is to generate shippable code. We really do hope that we can not only prove that our implementation of TLS has none of the flaws, but we also want to generate code that people can integrate into their products. So I know that it's pretty ambitious, but our dream is that one day we can walk up to the Firefox or Chrome or even, who knows, Internet Explorer people and tell them, hey, would you please use our code? It's written in C. We would love for you to integrate it. And there's no way we're going to get Internet Explorer to use an OCaml library. I can see myself, going to some Windows hacker and telling them, hey, look at that great language. It has functions and functors and polymorphism, and the runtime system is really great. The GC is really fast. That's not going to fly. There's a big culture clash that Andreas was talking about just recently. So there's no way we're going to get people to use an OCaml extracted version of TLS. So that's one of the reasons why we want to go to C. So my first reaction was face screaming fear, and it's 2016, so I put emoji in my presentations, but really we're gonna have to do it if we wanna get people to use our code. So that was the second bit, social reasons. And I should actually mention the first bit, which is performance. So OCaml is usually pretty fast, and I'm a big fan of OCaml myself. I even maintain the installer for Windows. But it turns out that the big performance bottleneck when you do cryptography on the internet is the cryptography itself, not the protocols. The protocol, it doesn't really matter that much if you take a little bit longer in exchanging the messages and the setup of the cryptographic parameters. But once the cryptography is set up, then you start encrypting lots of data. And there's a lot of math, including big nums, elliptic curves, hashing algorithms, encryption algorithms, etc. that are written in really hand-optimized C that are optimized for specific elliptic curves, and these use machine integers, and we don't have machine integers in OCaml, we have boxed machine integers. So we have some cryptographic code running in OCaml right now because F* extracts to OCaml, and it's just too slow. So that's also one of the reasons why we're going to C. So the architecture is as follows. We have F* that passes your code to a separate tool called Kremlin, and then you get C or C++, and you interact with the external world. Daphne is also using the tool to generate C or C++. So I'm going to cover the following bits. First of all, I'm going to tell you a little bit about the theory behind our translation from a subset of F* to C. I'm going to tell you how it actually looks like when you write code to extract it to C, and then I'm going to give you a little demo. Right, so quick overview of the theory. The pipeline is as follows. We have F*, which already has an extraction and erasure mechanism in the cell of coq, and then once you've done that, you end up in a subset of F* called low star, which I will tell you about in a minute, and our body of theoretical work has a simulation between low star and C*. C* is an idealized version of C that is much simpler and much more like a subset of C, and then this is to do. We haven't formalized it, and the proof that C* actually matches to, say, C light from ComCert has not been done either. It's to do. So what I'm going to talk about is the purple circle, the simulation between a subset of F* and an ideal version of C called C*. So low star is a low-level first-order fragment of F*. So in a sense, you have to think as if we offer you a curated subset of the C features. You can't take the address of anything. You can't dereference anything. It's not like other works which expose the full generality of C. What we expose is extremely simple. We expose stack-allocated buffers, no heap allocation, and locally mutable variables. You write your code in F* against a hyperstack library that models what the system C stack is, and if your code verifies its pre and post conditions, then you get memory safety. And if your code, matches all of these requirements, and if your code, doesn't use high order, doesn't use advanced features, then it qualifies as low star, and we know how to translate it to C. A word about low star, the way it's defined on paper. It's an expression language, semantics by substitution, and the memory model maps is a stack of frames, and each frame maps a buffer ID, because buffers are allocated on the stack, to a list of values. The semantics look like this. You don't have to look at it, just see that there's little brackets that say substitution here. C*, which is our target language, is much closer to C. It's a statement language. The semantics have these little things called continuation context, where you say, please evaluate the result of that expression, then store it in the map of local variables. So it's much more imperative. There's pointer arithmetic for buffers, and it's a much lower level language. The simulation between the two, the results that you usually want to have is that if E is your low star expression, so that's the high level language, and it's in relation with the C* expression S, statement, then you want to show that every compilation step that happens at the lower level is justified because it was an acceptable behavior for the higher level program. So any reduction step of the C* program corresponds to an admissible sequence of reduction steps for the original program. In more casually, the C* program only does things that were allowed in the first place. But this is technical and more difficult to prove, because in the case that the lower level program does a step that doesn't correspond to any step of the higher program, because say it's doing some low-level stuff, it's doing some intermediary dereference of a pointer, then you don't know, you cannot exhibit directly a state of the higher level program that corresponds to the step you just took. You just have to think about the case where n equals 0, and then your R is a very subtle invariant that says either I'm in the middle of doing something and I'm going to reach an S prime prime state that corresponds to an E prime state, or I have reached that state. So what we do instead is we use the CompSearch style, where we show that if I have a high-level step, then I can compile it to a series of low-level steps, and that works if C star is deterministic, that's the case, and if low star is safe, that's the case as well. So that's basically the little formalization that we have on paper, and that justifies that we can translate from low star to C star. So the whole thing makes sense. Why are we going such great length? Well, we want not only safety, we want to know that if your program in low star was verified to be safe by F star, you don't mess up your memory, you don't have out-of-bounds access, then of course you want the result to hold for the generated C program. But there's also something more important. There's traces, right? So right now, we not only have preservation of safety, but we also have preservation of traces. Traces being branches and memory accesses. And that is of paramount importance for cryptographic code because of side channel attacks. So you probably know that when you branch, you may reveal some information. So if you manage to show that your program in the first place did not have any side channel leaks, then you want to make sure that the resulting compiled program does not have side channel leaks either. And one piece of work that we're just tackling right now is that we want to show that we can have some degree of side channel resistance using parametricity. So the idea is that you have a secret type alpha, a value X of that secret type alpha, think private key, and you have a program that manipulates values of type alpha through a certain interface I. And the interface I is safe in the sense that, it won't allow you to figure out what is behind the alpha. You have two values of type tau, and you want to say that if you substitute an actual secret for X with an actual type tau for alpha in your program, then you cannot distinguish the execution of the program E with two different secret values. And you can obtain that sort of results using parametricity, because if I satisfies suitable conditions, then you can show that E has no way to distinguish between two values, V1 and V2. And that way, you can show that E was side channel free, and then the compiled program is also side channel free. That's also one reason why we really need to have these theorems. So that's about it for the overview of the theory between low star and C star. Let me give you a glimpse of the code and show you how it actually looks like when you're programming in that subset. So the memory model is a list of stack frames. You have a tip, which is the current stack frame. Each stack frame is a mini heap that maps locations to values, and you have special calls called push frame and pop frame that indicate that you wish to enter a new stack frame. So that's a test function that has the stack effect, and it returns unit, no particular precondition, no particular postcondition. That is a stack allocated buffer that allocates a buffer of size 2 whose initial value for each cell is 21. And I'm printing the addition of the first cell of the buffer and the addition of the second cell of the buffer. How am I going to guarantee that, say, I can't return a pointer to B, to my caller, which would be like a memory error? What happens is that the definition of the stack effect is complicated. You don't have to read it, but it says that any function that verifies in the stack effect satisfies the equal domains predicate. And the equal domains predicate says if your function buys into that whole stack modeling thing, then first of all, it doesn't change the top of the stack. Second, it doesn't change any other stack frame. The set of stack frames remains the same. And for each stack frame that was already there, the function did not allocate in any of these stack frames, which is impossible per the C model. So if that function satisfies all of these requirements, that's a function we can compile as a regular C function. And if we go back to the previous example, you see that this function wants to allocate, and the only way it can do it is indicate that it wishes to enter a new stack frame. It allocates its stuff in the new stack frame and pops the stack frame, and everything else is preserved. Therefore, the function can be compiled as a C function. We have some other neat tricks. Let's imagine now that you want to have a function that does a generic piece of code. Let's imagine, for the sake of example, that in cryptography, you'd often allocate a buffer of size 2 with 2 random values in it. You want to return that buffer because it's a generic piece of code. How are you going to do it? Well, we have a special stack inline effect that says that a stack inline function is allowed to allocate in the topmost stack frame And that function can be safely compiled to C as long as it is inlined in its caller's stack frame. So that function returns a pointer to a stack allocated buffer, but that's fine because the function has been proven sound as long as it is inlined in its caller's stack frame. So that's the kind of tricks that we can do with the modelization of the stack model in F-star. A little word about the tool now. How am I doing on time?
From 10 minutes.
Okay, good. So a word about the tool. We have F-star, which has already, as I mentioned, an extraction and erasure mechanism. And at this stage, once we've performed the extraction and the erasure, we dump that AST, and the external tool called Kremlin takes care of it. So Kremlin performs a bunch of simplifications in order to make sure your program eventually ends up in low star. In particular, Kremlin will lift nested lead bindings. It will make sure that all of your if-then-else's are in statement position, because that's something that only works in C. It will inline all of these stack inline functions, so it's like a mini compiler. And eventually, once your program qualifies as a low star program, the tool will perform the translation that I just talked about, and we will pre-print it as C. And then you can have an external compiler take care of it and take it from there. So I think now it's time for a little demo. Right, so that's the last bit. Kremlin is written in OCaml, and one of the next steps is definitely to prove it in F-star. It's a prototype, that's why it's a progress report, and the prototype is written in OCaml, so I'm pretty sure there's bugs in it. All right, so that's a little program that I wrote for this workshop. It's exactly the demo that I talked about. You have the test1 function that executes in its own stack frame and that is shown to have the stack effect. You have the test2 function that can only be verified to have the stack inline effect because it returns a pointer to B, so it will have to be inline in its caller, and you have a main function that has the stack effect. It returns an int, and it does something a little bit funky. It prints a randomly generated int32 with a bunch of nested let bindings and an if. It calls test1, and it also calls test2. There's a function called print int32. This one is defined in the externals module. The external module exposes a function without any implementation, and then I provide the implementation for print int32 in C, and then I'm going to call the Kremlin tool on all of this. I'm going to say Kremlin ml16.fst. I'm going to also provide the native implementation of the functions that I need, and then I'm going to say no prefix ml16 so that there's no prefix to the main function, and the main function that I wrote actually is the C main function. Kremlin does a little bit of auto detection, calls F-star, takes the output of F-star's erasure, and then will generate a bunch of C files in the current directory and compiles them. So all files linked successfully, thumbs up, and then I'm pretty sure that I can run this. Yes, so I get 1 for the first function, 42 because I did the sum of 21 plus 21 in the buffer, and then I have another randomly generated number.
Can you show us the C code?
Yes, it's here. So here's the C code. So one of the goals, we are trying as hard as we can to make it readable. So that's the buffer B of size 2. I have to do a for loop if I want to initialize its cells to 21. If I had okay, I should show you both side by side. All right, so test1 is generated as follows. You create a buffer of size 2, and the initial value is 21. So here you create an int32b of size 2, and you do a for loop to initialize each cell to 21, and then you call the external function print int32, and you print the 2 subcomponents. The main function has been rewritten quite a bit. All of these inner let bindings were lifted at the top level. SID is defined as a top level function. The srand call has been lifted from within an expression to a statement position. All of the other intermediary variables have been also rewritten. There's an IT variable to account for the if-then-else that was in expression position. And then what you can see here is the inlined version of test2. So test 2, because it returns a pointer to its stack allocated buffer, has to be inlined, so that's precisely what happened. B is initialized to 0, and then we put 2 random values, and then we print the sum of these 2 random values, and we return C exit success. Yes?
You said you were trying to make the SQL efficient, readable. I understand if you want to make it efficient or easy for DCC to optimize, but why do you care whether or not?
It's one of the weird constraints that's not very... Yeah, sorry. The question was, why would I bother about making the C code readable? Why don't I just dump, anything and then let the C compiler take care of it? That's not a very scientific reason, but if we want people to use our code, we want people to be able to... If we want people to use our code, we want these people to be able to read it and to do a manual review to a certain extent of the code that they're about to integrate into their product. So... Yes. So, it's half readable, right? You recognize the structure. There's a little bit too many macros right now, but it's getting there, right? So you can still follow along, right? The variable names are preserved. You can see the control flow that is preserved to a certain extent. And we hope that people, if they can read the code, can convince themselves that, they want to integrate it. All right. Demo time is done. So just to briefly conclude and to leave some time for questions, our approach is a much more restricted approach than other things that I mentioned in the first part of this talk. One way to sum it up would be a shallow embedding of C into F star with a curated set of operations, such as buffer allocation on the stack, locally mutable variables. We have written, I have not, the PhD student at INRIA has written 12,000 lines of F-star code that proves big number arithmetic, several cryptographic elliptic curves and their operations on the curve. He has written 2 cryptographic constructions called Cha-Cha-20 and Poly1305 in that subset, and one that combines the 2 called AEAD, which is a cryptographic thing that does authenticated encryption with additional data. And that code extracts to C, compiles, and runs properly. So we will very soon release Hacklestar, which is high assurance crypto libraries, which are written using this tool and allow you to have verified cryptographic primitives. Kremlin is open source. There's already F-star and Daphne that are using it, and if someone in the room wants to connect another language, such as Coq, to Kremlin and reuse the same approach to generate C code, I'd be more than happy to help. And hopefully very soon we will extract more code, including the entirety of the MeTLS library, so that we can walk up to our friends on the other side of the highway who work in Internet Explorer and tell them, hey, will you please use our code? All right, thank you.
Questions?
Yes.
I'm Vidaka. I work in the Cogent project as a verification engineer. And in that project, system engineers wanted Cogent to compile to human-readable C code.
Yes.
And they experienced strong pushback from the language side. So probably you want to talk with our language people why they don't want to compile Cogent into human-readable.
Shall I repeat?
The idea is you want the code to be efficient and have a shallow embedding that people are supposed to be reading rather than the C code.
Well, but I mean, there's a culture clash, as Andreas was talking. I mean, you walk up to a C++ engineer and he's like, let? You don't have a loop? Where's your loop? Recur what? That's a big social problem. I mean, I agree that our life would be much better if we could, but the other idea behind this very shallow embedding in F-star is that the performance model is very predictable. You know when allocations occur, you know where your things are allocated, so you control the performance at the F-star level already. So you don't need the tool to do a whole lot of rewritings. What the tool does is, it allows you to use as many niceties of ML, like, an expression language, inner let bindings, and then the tool will massage it so that it fits in C, but there's not a big distance between what you write in F-star and what ends up in C. But I agree that it's a weird constraint, right, having human readable code, but that comes because we're trying to.
For
distribute it.
It's already a constraint that is good for code, for example, when code is back to a camera. It's a constraint, and it's very important that the code which is generated is somewhat readable.
Yeah,
Because you want to integrate it in code written in OKR.
I understand the constraint there, because I mean, from my perspective, this is the output of the like C is the output of the star compiler. But for OCaml, I mean, I understand this a bit more if you want OCaml code to be readable, because you want to integrate it with existing OCaml code.
That's the same here. We want to integrate it. Okay.
I see.
But sorry, time is over.
One last.
So the last question.
Okay, so could you say just a little bit more about the use of parametricity to improve like the information flow properties, the side channel resistance? How long are you in that?
There was something in.
Repeat the question.
Yeah, the question was basically this. Can you say a little bit more about this? There's a paper where Cedric had a similar technique, and basically you have to define a notion on I that none of the functions in the interface are destructors. So basically you don't want a function from alpha to bool. Alpha to alpha is fine, unit to alpha is fine, but alpha to something that is informative. So you have to define a notion of what is informative or not, and then from there you have to do a logical relation that says that for two execution there's no way you could possibly distinguish them. Happy to talk about it afterwards. Thanks.
Thanks for coming.